bespoke radio for the masses.
Headline edition, July 8, 1947. The Army Air Forces has announced that a flying disc has been found and is now in the possession of the Army.
If the game is rigged, change the game. Game changer.
I occasionally think how quickly our differences worldwide would vanish if we were facing an alien threat from outside this world.
This is Fade to Black with your host, Jimmy Church, on the Game Changer Radio Network.
All right. Good evening, Fade to Black. How you doing? It is Thursday, February 29th, 2024. Very excited about tonight's show. And now, as we get started here, the fans of this show that have been following this show for a decade now know that I have a passion for two things: the completely strange and woo-woo and science. And the more that I see and feel and know crazy woo-woo things, the closer it pushes me into science. And the two are on their way to a train wreck. The two are going to collide. It's just the way that it is. And with the thousands of shows that I have done, it's always pushing me into the science, and the science helps me center things. It's just the way that it is. And that's why tonight's show is so special. Tonight we have Dr. Paul Sutter with us, and I titled the show, it sounds strange, Astronomy, Science, and Society. Now, I could have gone in any direction, but I think that's going to frame up our discussion tonight pretty well, because we're going to be discussing astronomy. We're going to talk about the universe. I'm going to manage to get ET and contact and time travel and all of that other stuff into the conversation tonight. And what is it that science knows? And how does that knowledge get to us, the community, the world, and society in general? And why is there a seeming breakdown in trust with actually both camps? So we're going to do all of that tonight with Paul. He is a professor in physics and astronomy at Barnard College, Columbia University. He's an advisor to NASA. He's an author. He's a host. He's an award-winning science communicator. He's also a U.S. cultural ambassador. His website is below, pmsutter.com. It's also on our website and on social media. Let's get straight to it and say welcome, Paul. How are you, man?
I am good. It's a late night here for me in Connecticut, but I'm willing to do it for you.
Yeah, well, you know what? That's a good start. Are you okay? Before we get too far into this, you have to get the first-time guest disclaimer. So let's get that out of the way. Next time you're on the show, and we're already going to book that probably before the end of the night, you won't get it, but you get it now, which is this. Paul, it's just you and I sitting on my couch having a conversation as friends, and where that conversation starts, it starts. Where it ends. But we're going to end as friends. But you have to accept.
I accept. Well, how far apart are we on the couch? Are our knees touching? Is it weird? Or are we on opposite sides with our arms like this?
Right. There's
I need to understand the parameters.
A rolled up newspaper between us.
Fair. Deal.
Yeah, okay, good. Okay, I'm more comfortable now too. I want to start. I want to start here. There was an announcement. Now, I may have some of the parameters off a little bit, but in a nutshell, there was an announcement, a press release from the AAS. I'm assuming you're a member, the American Astronomical Society, last month with a statement that said we need protocols in place on how to deal with trauma that may be caused when an astronomer sees something alien out deep in the universe for the first time. And now I'm reading the press release and I thought to myself, okay, what is it that they know that we don't? That's the first thought. But the second thought is, yeah, if they feel the need for that, the trauma and, looking through and seeing something crazy for the first time, some technical signature, somebody's going to freak out a little bit. Are you aware of that press release? And are there conversations inside of the AAS about this?
So as you were asking me, I was so curious about this. I've never heard of it before. I started searching for it and I cannot find anything about this press release. I'm not an active member of the AAS, which is how you say it when you're trying to be cool. You don't say AAS, you say AAS. That's how you fit in with all the other astronomers. So I'm not an active member. I have been a member in the past, and I've floated in and out of membership. I've attended the biannual conferences before. Usually don't, because I'm usually busy. But it is the major professional society of astronomers in the United States. I have not heard a single thing about this.
Okay. Have you thought, okay, now that's actually a great start, because that allows me to ask this question. Have you ever seen anything strange that you can't explain?
Yes. And in fact, that is my day job as a scientist, because if we were to be able to explain everything that we see in the universe, I'd be out of a job. There'd be no more need for science. There's no more astronomers, no more physicists, because there's no more mysteries. The entire endeavor of science is a study of natural phenomena in nature and trying to explain it. We are surrounded by mysteries. We are surrounded by things we don't understand, which is why we go out with our telescopes and our accelerators and our chalkboards and our minds and our curiosity to try to understand that mysterious universe. So yes, almost every single data set I work with, or observation I participated in, or theoretical insight I push forward contains more mysteries than I can solve in a lifetime. And that's the beautiful part to me.
Do you remember how science was framing itself about 150 years ago, in that there's nothing else to learn, right? We've got it all figured out, and where we have come since then, and I say it every day, we've got more questions now than answers, and that is pure science, isn't it?
Oh, absolutely. And most scientists, I forget the scientist who said that. It was a late 1800s. I want to say it was Rutherford, but I could be wrong about that. Say, okay, we're almost done. We've got a few more details to clean up, and then we can all retire and go to the Bahamas. But obviously he was wrong. Most scientists at the time did not believe that. When he said that, the great irony of that quote is when he said that we were on the cusp of several great revolutions in science. We are on the cusp of the quantum mechanics revolution, the relativity revolution, the cosmological revolution, understanding the Big Bang. That's just in physics and astronomy. There have been so many wonderful insights over the past 100 years that science is this joyful search in nature. It is this thing where we are always learning new things. It's part of one of the most beautiful parts to me about being a scientist, is that there are centuries of thought leading up to our current understanding of nature. And yes, we view the universe very differently now than we did 50 years ago, 100 years ago, 400 years ago. And our knowledge is constantly updating, constantly changing, constantly provisional. We're always gathering new evidence. We're always seeking deeper understanding. And I know we are not at the final answer, because there is no such thing as the final answer. There's always more to learn in the universe. And I hope 50 years from now, 100 years from now, 1,000,000 years from now, we look at the universe a different way than we do now. And the joy to me is being a part of that tapestry, to getting to write one chapter in that grand story of this human tradition that we have built, dedicated to the exploration of the universe.
But why do you keep the good stuff to yourselves?
Well, I know, right? So scientists, I'm going to be honest with you, scientists, we're in a pretty rough shape. Funding for science, and I'm talking about fundamental, basic research science, the kind of science that does not have a guaranteed result, the kind of science that is not attached to for-profit enterprises. Like we're talking like very, very basic theory, very basic astronomy, and many other fields of science is almost entirely supported by your tax dollars, by the federal government, by institutions like NASA, the National Science Foundation, National Institute of Health, Department of Energy, various agencies. That funding has been flat or declining now for about 30 years, dropping as a share of overall federal expenditures. And so funding for science, for basic research in our country, has actually been dropping for a generation now. Scientists and research scientists in academia who are trying to just figure out the universe and make guesses and develop hypotheses and test them. We are facing ever tighter funding constraints. We are having to fight each other more and more to get funding. And one of the unfortunate side effects of this is that the vast majority of scientists are not incentivized to communicate their work to the public. They are not incentivized to reach out and share what they have learned. And I believe that's a mistake. I believe that the public, because they are the number one source of funding for science, I believe it is ultimately owned by the public, that what we learn as scientists, it belongs to the nation, to the world. I do believe it is the moral and ethical duty of every scientist to communicate their work to the public. But when you are a scientist actually trying to advance in your career, you're trying to get positions, you're trying to get promotion, you're trying to get tenure, you're trying to win grants and hire students, the more you do outreach, unfortunately, and it pains me to say this, the more you do outreach, the more you are punished. You are less likely to win grants. You are less likely to get tenure. You're less likely to be able to hire students and win awards and grants the more you communicate your science. And so we have set up a culture as scientists, as the institution in the United States, of an academic institution that is becoming more insular with time, that is guarding itself more and more against the public with time. And I believe this is one of the many reasons we are seeing deteriorating trust between scientists and the public.
Well, the running quote about NASA, right? It stands for never a straight answer. And that it's kind of earned in a weird way, but for the reasons that you've just stated. And there was another press release. I do the news every day. And I didn't realize this, but when you look at the hard numbers, people ask, well, why haven't we been back to the moon? Well, okay, there's the conspiracy side, which is probably the truth, but then there's the numbers side, and the numbers side is in 1970, the Apollo program, NASA had 5% of the national budget. 5% of the national budget. Today, NASA's budget is 1/10 of that, and trying to go back to the moon and Mars and Jupiter and Saturn missions and everything else that is being funded right now with 1/10 of the budget that they had in 1970. So with that comes communication, PR, right? All of those budgets are pulled back too as well. I'm not making an excuse for NASA, but it's exactly what you're talking about, isn't it?
Absolutely. It's funny you say never a straight answer. I drive my family nuts. They ask me a question and I can't help it. the universe, when you ask a scientist a question about the universe, like how does this work? Why does X cause Y? What's going on here? It's always a complicated answer because we live in a complicated universe. I'm not responsible for the design of the universe. I'm just the messenger. I'm just the one trying to figure it out. It is a complicated, messy, nuanced place that we find ourselves in. Often simple answers can be deceiving because they can sound very good, but they hide a lot of the real nitty-gritty details. And so, yeah, scientific answers are always going to be nuanced. They're always going to contain caveats and assumptions and uncertainties and error bars because that's the universe we live in. And you make an excellent point about NASA's budget. We haven't been to the moon recently up until this past week, the landing with the Intuitive Machines autonomous lander. We hadn't been back to the moon in half a century because we don't want to spend the money on it. In the 1950s, 60s, and 70s, we had the political will for it, where we could spend a tremendous fraction of our money, of our federal budget on the moon landing. That was completely unsustainable. We could not keep up that level of expenditure decade after decade after decade. The public didn't want it. Lawmakers didn't want it. And so NASA's funding got cut. It's just, we don't have that kind of money to play with anymore, which in many ways is good because now as we are attempting to return to the moon on a more permanent and sustainable basis, we have to be more clever about it. We have to be smarter about it. We can't just throw so much money at it to just solve every problem and then cross our fingers and hope something doesn't blow up. We actually have to be very, very careful. We have to be very miserly and very clever. And this is helping us. I believe this is a healthier ecosystem for especially private space companies because it allows us to do it in a smart way that means we don't just go and visit for a few days and come back, that we can actually develop a sustained presence on the moon and hopefully further out in the solar system. NASA, I have many, many friends in NASA. I serve as an advisor for a NASA program. And one of the hardest things about NASA is the vast majority of their budget is directed by Congress. Which means every year or almost every year when there's a new congressional budget, most of NASA's budget expenses every year is line item decided by Congress. And that makes it largely impossible to have any kind of sustained effort because things can change year to year. Already there are issues because of the continuing resolutions and the budget problems that we're having in Congress right now in order to pass a long-term budget. Already we're seeing the ripple effects in NASA where programs are having to get paused or canceled or, oops, you missed your launch window. You're going to sit in a warehouse for another 3 years until the launch window opens up and things like that. It's a very, very difficult environment for NASA to operate in, which is why I'm a very, very interested and watching with a keen eye the explosion in private space industry. And it's just amazing to see what you can do when you have some admittedly very wealthy people and very eager people willing to shell out the money and willing to hold on for the long term. That's pretty cool to me.
Are you part of the James Webb?
I'm not. So my particular research interests don't 100% align with the James Webb. There are some ways to inform my research with the James Webb, but not directly. But I'm much more involved and more closely paying attention to a follow-up astronomical observatory, an orbiting observatory called the Nancy Grace Roman Telescope, which is set to launch in a couple years. And that is a cosmological observatory. That is going to serve as a map of a good chunk of the universe. And by good chunk, I mean like 0.1% of the volume.
Yeah, it's gnarly. I mean, I don't have a better word for it, but that is the coolest piece of machinery I have ever seen. But let me ask you about the James Webb Space Telescope for a second. Let's suppose it finds a technical signature. And let's say of an exoplanet, something extraordinary, something crazy like dimming lights of a city on a day to night thing, right? Okay, something. I mean, like
weird.
crazy. Yeah, something crazy, something real, right? Does that filter directly to the public once confirmed, or would there be a government interference of that information getting to the world?
So astronomers don't work for the government, and the vast majority of astronomers do not work for the government. If in the vast majority of observing time with the James Webb Space Telescope is not filtered even through NASA. So what it is, James Webb, most of our large observatories are relatively open access. They're just platforms. It's a big telescope in space, and you can apply for time. You can say, hey, I've got a cool idea. I want to take the James Webb. I want to take 10 hours and I want to point it over here. And here's my research case. You can apply. There are annual cycles where anyone in the world, astronomer or not, can apply for time on the James Webb. When you get your time awarded and you get your allocation, like, okay, on March 10th, you get 10 hours of observing time. Go, do whatever you want. Just don't point it at the Earth, because that will melt the thing. So, be careful. You collect the data passes through, and the raw astronomical data is exceedingly messy. It's noisy. There are artifacts. It's this massive pipeline. That giant pipeline is sent to you, to your servers, to your computers, and then you have it. It's just sitting there. And then it's your job as an astronomer, and this is the real hard part of astronomy, to clean up the data, to analyze it, to get something sensible out of it, to actually understand what you got with that 10 hours of observations. The James Webb is just going to give you the dump of every single information, all the photons that hit those mirrors during those 10 hours, feeds it back to you. It's your job to make sense of it. So if you see something interesting as an astronomer, it's yours. The data is sitting on your laptop. And so presumably, if I had to guess, because we've experienced this before, not like techno signatures, but we've seen very, very cool stuff in the universe before. And we've seen a lot of cool surprises in the universe before. So usually what happens is you get the data and you analyze it. You're like, oh, that's weird. I probably did something wrong. And so you apply for time in the next cycle and you make the observation again, just to make sure you're not crazy or there wasn't a weird artifact. If you confirm internally that there is something interesting here, maybe you share it with some colleagues. Maybe you walk it down the hall to your friends. Say, hey, Carol, could you look at this? Like, this looks a little fine. Can we talk about this? Maybe you talk about it within your department. Maybe you email some friends across the world. If it's a very, very large announcement, you're going to want to claim ownership of this. You're going to have a scientific paper attached to it. You will submit it to a journal. The journals will usually, again, this isn't required by anyone. This is just normal practice. Will say, okay, you've got something big. We're going to run it through peer review. We're going to get it vetted, or at least the first round of vetting. We are going to alert the world that there is something big here. We'll hold a press conference. We'll embargo the results until a certain time so that we can make sure we can pass peer review, editorial checks, and then we'll do a big announcement to gobble up as much attention as possible. Why are all these agencies and institutions and individuals trying to carefully navigate the chess pieces to make as big an impact as possible? It's because they want to get it right and they want to make a giant splash, because guess what? The first person to get a reliable detection of a techno signature or anything huge, anything big, that is fast track to worldwide fame, name in the history books, Nobel Prizes, the works. This is like, scientists are very self-motivated. We want to understand the universe, and we also want to get accolades and awards for our hard work.
You would have a religion named after you.
There you go. That'd be great.
But which is an even greater reason, I would think, to keep that from the public. We've all seen the movie Contact, right? With Jodie Foster, and she gets everybody involved. They do, and what happens? And I think that's one of the other great fears when it comes to trust. It's like the Pandora's box, not only of this community, but of the world, right? The big announcement, we're not alone in the universe. Well, when did you find this out? How long have you known, right? These are the follow-up questions to a statement like that, right?
Mm-hmm. Oh, yeah. And it's hard to sustain conspiracies when you have more and more people involved, because by the time.
So you're saying there are conspiracies?
Well, no, like they're conspiracy in the very, very general sense.
Yeah, I've just
two or
messed
three.
with it.
Yeah. So like by the time a data set like that is polished and cleaned and analyzed and studied, there are dozens of individuals who have looked at this result. There are the principal investigators, there are collaborators, there's grad students, there's postdocs, there's people in other institutions, there's editors of journals, there's anonymous peer reviewers. And if there is an attempt to hush this up, all it takes is any one of those to put it online. And in fact, almost all astronomy goes online for free. If you go to the archive, arxiv.org, it is an online repository of almost every single paper that has been submitted to any journal in physics and astronomy for going on almost 35 years now, all the way since the early 1990s, all available for free, 100% free, 100% public. You can access any journal article written in a quarter century.
I spent so much time on archive. That is, I'm in a 12-step program actually with archive. It's and staying on this for a minute, if we may. If we continue with the exoplanet count, and with the addition of Grace, and we have Tess, and we have James Webb, and of course Hubble is still, Hubble is hobbling along and still producing results. With the exoplanet count, and with the next stage of exoplanet searching that gets launched, we are now talking about scans of below Earth. Well, I don't want to get technical with everybody, but we're looking at sections of the sky, and there's so much math that is involved with every single star that is being examined, right? With all of it, it's a tremendous. But now we have the computing power and the algorithms to get this done at a mass scale, and we have a backlog now of confirmations. We have the confirms, right? But the potentials and the probables, it's like thousands a day, right? It's just like crazy. It's just getting more. When now we understand that every star in the universe has got at least a planet in the universe, right? That's crazy. When just in 1995. We still only had us, right? The count was 0 in 1995 with exoplanets. When you look at it like that, how much life is out there when it's a numbers game that seems to go to infinity?
So quick clarification, in 1995, there was at least one known exoplanet. The first exoplanet was discovered all the way back in 1992, actually.
That's
and it was
correct.
around Pulsar, around a dead star, which is super crazy. They got a Nobel Prize for it, well-deserved. And you're right, the number of known exoplanets is increasing all the time. The biggest treasure trove of exoplanets we got was from the Kepler Space Telescope, which is since retired, but it alone got 6,000 or 7,000 candidate exoplanets. Most of those have been followed up with ground-based observations to confirm those detections, and there's still a couple thousand more that are left. Right now, we have the successor to the Kepler. We have the TESS, the Transiting Exoplanet Survey Satellite. I think that's what it stands for, which itself is designed to gather thousands of exoplanets. The James Webb isn't a survey instrument like that. It's very, very pinpointed. It's so high resolution. It only looks at a tiny, tiny part of the sky at a time. So it's not really a discovery tool for exoplanets. It's a second look instrument. Like, oh, you found an interesting exoplanet that might be in the habitable zone. It might be Earth size. Let's hone in on it with the James Webb and see if we can get some more information about it. One of the major great observatories coming up in the next decade or so is something called the Habitable Worlds Observatory, which is going to be geared to find an Earth 2.0, to look at 10 to 20 near solar system objects. We're talking about objects within 20 or 30 light years of the sun, and specifically try to characterize the atmosphere of Earth-like planets to look for signs of life. That's that targeted direction to pinpoint, to look for signs of life, to look for planets orbiting stars that might harbor life, and really, really study them in detail. And then there's another side of it, which is let's keep hunting for exoplanets and try to bag as many as possible. The Nancy Grace Roman telescope that I mentioned, which is primarily a cosmological instrument, will also be an exoplanet hunter using a completely different technique. With this instrument, we expect to get around 1 million more known exoplanets. The estimates of exoplanets in our Milky Way galaxy range on the low end from a few 100 billion. So roughly one planet for every star. The high end for exoplanets is somewhere around 10 trillion. So quite a bit of uncertainty there. The end result is that there are a lot of planets in our galaxy. There are a lot of galaxies in the universe. Therefore, there are a lot of planets in the universe. We have so much information already about these exoplanets, not just the faint detections. We actually have direct imaging of some of these exoplanets, like literal pictures where we've blocked out the light from the star and we can see the infrared radiation coming from the body of the planet itself. It's like crazy. When it comes to aliens, right now, we have no scientific evidence for the existence of aliens. We've looked really hard. We haven't found anything. That's a scientific answer. On a personal answer, man, it's a big universe out there. It makes me feel a little bit too cold and alone and isolated to think that this is all for us, that we're the only intelligent civilization in the universe. So I like to think that there are aliens, there's other life, there's intelligent life out there. But the scales of time and space that operate in our cosmos mean that we are effectively alone. At best, we may get some faint signal here or there, some little bit of evidence to show that there was perhaps in the distant past the existence of some aliens. Things like active communication, active transport and movement is pretty intense, not impossible, but pretty intense. And so, that's okay to me. Like, just knowing we're not alone or believing we're not alone. Again, that's just a personal belief of mine, not backed by any evidence. It's just a feeling, and it helps me sleep at night.
Well, I went out to dinner with Avi Loeb And he was on my TV show, so I got to spend a couple of days with him. And we were at dinner one night discussing this. And now I'm not saying I can match brain power with Avi, but I did my best. But he also corrected me on a couple of things when I was throwing numbers out when it came to the amount of planets in the Milky Way. And I was throwing numbers around 40 billion. That's what. And he said, no. And he said, it's probably closer to a trillion. Now, a trillion is a number, Paul, as you know, we throw it around too easily without really truly understanding how big of a friggin' number that is. That's 1,000 billion times 1,000 million. That's an insane amount of stuff. And therefore, it becomes a numbers game. And Avi went back to me and he said, man, even if we're talking percentage points, we are dealing with 100 billion rocky Earth-like planets in the Goldilocks zone, smack dab in the conservative Goldilocks zone with water. And now I'm not here, I can't argue that point with Avi, but when you think about it like that versus where we were, 20, 30 years ago with that kind of thought pattern, things have really, really changed, haven't they?
Oh, yeah. Exoplanets is one of those things where astronomers we've always suspected there were planets orbiting other stars. We thought there was no reason why our solar system should be special in any particular way. But we hadn't had the data. We didn't have the confirmation. And now that we have thousands of known exoplanets with masses, with distances, even some we can characterize the atmospheres of some of these exoplanets. We can start to build a census. We can start to get some demographics. We can start to get a handle on that. And yeah, the general consensus in the astronomical community, again, this is largely guesswork based on the few thousand exoplanets that we know of and general understanding of solar system and planet formation, is that there are probably a few billion, somewhere in the billions, Earths roughly the same size as Earth, orbiting stars that are roughly the same size as the sun, within the same rough orbital distance to put them in the habitable zone. So we're talking billions. And that is a number that we weren't able to have decades ago, simply because we had one known exoplanet, and it's very hard to build a census off of one sample. Now we're getting better and better at it. Once we have things like the Nancy Grace Roman telescope in a few years, it's going to be amazing. Like, once we know of millions of exoplanets, we'll be able to refine these numbers even more and more.
How do you resolve? I'm still working on this, by the way. I don't have an answer. How do you resolve the UFO conversation that is happening in Washington, D.C., and the DOD and Congress and Senate and military pilots and the tic-tac and the concern right now about stuff apparently visiting this planet? That has to come into the equation somewhere, and how do you resolve that?
Yeah, so it's not necessarily a resolution, it's more of a statement. If there are things in our atmosphere that have no good explanation, there are observations that has no satisfactory answer for what we are observing. We call these things UFOs, or more recently UAPs. The key word to me in either of those acronyms is the unidentified. We don't know. If you see something, there's like a radar return or a thermal signature or a report of a visual observation or whatever, there's some sort of detection of something that we don't understand. If once you say something like, oh, these are visitors from another planet, you are adding extra information that we don't have. You are adding assumptions. If we don't know, if it truly is unidentified, then that's as far as you can go. You can't claim an origin to it. You can't claim to know an identity or a background or a source. You need extra information in order to be able to make a statement like that. And right now we don't have that extra information. So when it comes to unidentified objects, I'm obligated as a scientist to remain in a state of ignorance, to say, well, I don't know what it is. And that's as far as I can go. With that lack of knowledge, with that sparsity of information, with this very like low quality data, we would say in science, there are numerous hypotheses, there are numerous possibilities. One possibility is that aliens are visiting the Earth. Another possibility is that we are misunderstanding these radar returns or thermal signatures, that there's some sort of mundane explanation. Another explanation is that a potential explanation is that some foreign power is developing some advanced craft beyond what we currently understand, or stealthing capabilities, or et cetera. So there's some Earth-based technology that one of our rivals is deploying against us. And so there's a list of possibilities. You can't, without additional information, you can't say which possibility is which. If it was aliens,
let me jump in. You can't. But those that are there that see this can. They have that observation and they have that ability to use discernment in the moment. You don't have data, and there isn't a radar return or any of that, but you don't have that data. But the witnesses, let me give you a situation, and this is an actual situation. This actually happened. All right. I'm sitting at a picnic table with 30 friends. I actually have 300 friends, but 250 are behind me at a conference, my conference. I'm sitting outside with a pair of binoculars on a tripod, and I'm looking at birds. Okay? I'm outside looking at birds. And sitting next to me is a friend of mine. His name is Steve Murillo, who graduated from the United States Naval Academy. Okay? Very smart guy, very cool dude. He's sitting next to me, and I'm looking at birds, and I'm looking at this mountain, and the mountain, which is Mount Adams, is 14 miles away. And I know this because I'm looking at it every single day. I know exactly where it is, right? This is a giant volcano. But I'm looking at the peak of the mountain, and I'm looking at the birds flying around. I'm having a peaceful moment to myself. And out of nowhere, from behind the mountain, remember, it's 14 miles away. I've got these giant binoculars on a tripod. I see from behind the mountain what appears to be a 500-foot tall beer can. And it's spinning like this. And it's black. And it comes out so here's the mountain peak. And it comes out from behind the mountain. I don't see it go past them. I'm looking at the peak. And I freak. And so it's black, and it had a round circle on it that you could see. And it's in the middle of the day. It's 3:00, cloudless, perfectly in focus. I see this circle. I see it spinning, and it's kind of silver on the bottom and the top, but it's black. Slowly spinning, and it's moving in this direction. And I don't even know how to react. And I jump up and I yell, video, pictures. And I come back, and Steve Murillo goes, I see it. Now, with the naked eye, Paul, it's this big. It's 14 miles away. It's just a black dot in the sky. But you can see it spinning because of that silver thing on the side. I go back to the binoculars, and I look at it. Now, about 5 seconds has passed. I go back to the binoculars, and I look at this thing. I absorb it, top to bottom, and it's massive because it's 14 miles away and came out from behind the mountain. And I can't explain it any better than this. This is what it is, right? And And I'm looking, and Steve goes, I see it, it's spinning. And I come back and I look at it with the naked eye, and I could see the glint. The sun is like over here. I can see the glint on that circle thing. I can see that. Now 10 seconds has gone by, maybe 15. I come back to the binoculars, and Steve said, it's in the middle of the sky, blue sky. It phased out. What? And it's gone. I didn't see it disappear. And I come back. I thought we were going to see it, Paul, for the next hour. It was moving so slow across the sky. This thing, and I'm guessing 500 feet by maybe 200 feet across, slowly spinning, appeared out of nowhere, and then now that is not, now I don't know what it was. It's unidentified for sure, right? That's the big U. But I can tell you that it disappeared. I didn't see it up here. I just saw it appear from behind the mountain. So the question is to you, with that kind of data, if you're sitting next to me and you see that, that's all you need, right? That's a real object in the sky. That's not a dirigible. It's not a balloon. It's not a helicopter. It's not a rocket. It's not a satellite. It's not a meteor. It's not anything. And those are the problems that we face today. Science needs to go and look at that and try to understand what we all witnessed. And there were 30 of us that saw it together. I have a recording of it. You should hear us. It's crazy. It's crazy. So I don't know what to do with that. And as an astronomer and a physicist, when you hear something like that, that's all the data that you really need to understand that the phenomena itself is real.
I don't know. I was not there. That's the reality is I wasn't there as a scientist. We have incredibly high standards of evidence, but we do not come to our beliefs in science easily. The example I like to use is that it took us 100 years to convince ourselves that atoms were real and that were a fundamental component of nature. It went from the early 1800s with the chemist John Dalton to proposing the modern scientific concept of the atom, all the way to Einstein in the early 20th century to proving their existence. And so it took 100 years of debate and arguing, like, is matter made of atoms, or is it more like a fluid? Is it a continuous substance? We do not come to our beliefs easily. That slowness of science, that carefulness of science is how we actually make progress, because we see strange phenomena in the universe when it comes to astronomy all the time. Like I said at the beginning of the show, that's our day job. Well, night job. That's just what we do.
Right, night job. Well, so let me ask you more directly. If you saw that, do you go and tell your friends exactly what you saw, or do you keep that to yourself?
I don't know. I haven't personally encountered something like that, so I really don't know. I'd probably tell my wife. Maybe I'd tell my kids. Maybe my cats. They like to listen to me. Maybe I'd tell my friends. I don't know.
Yeah, I know how crazy it sounds.
To the naked eye, I'm curious. To the naked eye, you said it appeared as a dot?
No. To the naked eye, Steve, who is sitting next to me in the recording in the video doesn't catch anything. They're pointing, but the audio is there. And Steve says, I see it. It's spinning. That's what he says. You can hear the chatter from everybody else. Yeah. So when I looked at it in the binoculars, I saw this. With the naked eye, it was a black spinning thing. Yeah, you couldn't couldn't see if it was tall or anything like that. But you could see there's a man. I swear.
No,
This
I'm
is the
just curious.
crazy part. It sounded.
I'm curious about the angular size of it. Like, if you were to hold out your, say, pinky finger at arm's length, how would it compare to the width of your pinky finger?
Oh, no. To the naked eye, here. I'll draw it for you. That's the mountain 14 miles away, and that's how big it was.
Like a tiny, tiny dot.
Yep.
So
but you could,
but you could resolve it with your naked eye.
Oh yeah. I saw it spinning myself. The whole event only lasted 10 or 15 seconds. And like I said, you can see it here. It was moving in this direction, right? It was going this way. And I thought it was wide open sky. We were going to see this forever and videotape it. It went from that and then gone. In the binoculars, it was a 500-foot tall beer can. That's the only way I could do.
And it was
crazy, man. It was crazy.
And it was 15 miles away.
14.
The mountain.
The mountain is 14 miles away, and so I didn't. Okay, this is actually good. The mountain has two peaks on it, and it came out from behind this peak. I didn't see it here. It wasn't like it came across like this. It didn't. I only saw it go whoop, whoop, from behind that peak. It was nuts, man. It was. I'm telling you, I know how crazy it sounds. I understand.
No, it's fine.
But it doesn't change the event. The event was real. Yeah, it was. It was
a little speck like that is about 1/10 of a degree, and if it was 14 miles away and 500 feet across, it would be much larger in your field of view. It would be about a little more than half the width of your pinky finger to the naked eye. So was that's just this is just angular size. Like if you put an object at a certain distance, that's the angular size it appears to be.
Right. Okay.
Yeah. So your object was either smaller than 500 feet. I get a rough number of around 100 feet, or it was
could be,
or it was further away. Could
be. So in the binoculars, let's do this. So in the binoculars, I'm looking at the peak of the mountain like this, and it was about this big. That's what I saw. Okay, so binoculars, I'm looking at the peak of the mountain, and it just came out from behind the peak, and it was that big looking at the peak of the mountain. So they give you an idea. And it was
what power were your binoculars? What was the magnification?
I've got them in there. Celestrons, I don't know, 1.5 feet long. Stargazers, the Celestron Stargazer, you know those. And on a tripod, it didn't, because of what my life has been like. I love NASA, the astronaut program, Mercury, Gemini, Apollo, all the astronauts, airplanes, helicopters. It's my fascination. I love these things. And I know what's in the sky. I live here in Palmdale. I live down the street from Lockheed Skunk Works, right? Out in front, they've got two SR-71s sitting there, right there a mile from my house. Edwards Air Force Base. I see all the crazy. I love aerospace. I love airplanes. This didn't fit. My brain just shorted out. It was pretty crazy to see. I still don't have I thought about it so much. And the other crazy part about this, and I do want to swing this back to physics when we discuss this kind of stuff, is that I would have rather have seen it disappear. Steve's description is in the video, it phased out. Now, okay, we can talk about all kinds of, but that part of it, and that's where physics comes in for me when, string theory and 11 dimensions and multiverse and parallel worlds and these different conversations that are going on today in the world of physics and theoretical physics. Is this something that just came and went and was only visible in our wavelength for a few seconds? And that it wasn't anything physical at all, or it was only physical for that time that it was in the sky. I don't know, but it phased out, and that was the other part. And I didn't see it do that, so I don't have a description of what that looked like.
I don't know.
Yeah,
I just a overheard sentence reported to me is not enough that's not enough data for me to operate on as a physicist. That's not enough to get my hands dirty and start working with it.
Yeah. No, I totally get that. The question that I always have with people with a story like this is that have never seen anything strange. There's a lot of people that haven't. They have, there's a lot of people that have. But if you saw something like that, right? If Anderson Cooper saw something like that with his own eyes, does he go on CNN and talk about it? Probably not.
You'd have to ask him.
Yeah, probably not.
I couldn't guess what he would do.
Yeah, it's totally strange. And so, and here's the other part, and we'll talk more about this when we come back. Einstein, when you look at relativity, it's not a big mystery. Relativity, everybody, is just observation relative to somebody else making an observation. That's what relativity is about. Now, it goes way beyond that, but basically, that's what it means. And so when we jump into that, Einstein said, and we base everything on this, nothing can exceed the speed of light, right? That's it. How is the conversations now are the faster than light conversation? It seems to be a pop culture term now, faster than light. Is it possible that, science is nothing but a series of corrections anyway? Is it possible that an object can exceed the speed of light, or is there another way to overcome the speed of light?
So this is a great question. So Einstein's special theory of relativity was a groundbreaking discovery. Other scientists at the time, we're talking early 1900s, were actually on the cusp of also figuring it out. Einstein was the first. Einstein figured out a lot of stuff that no one was even thinking about. This is one of the things that several other scientists were inching towards, and Einstein was the first one to crack it. And it's not that everything is relative, despite the name relativity. The key point of relativity is that measurements of time and space are relative to the observer. So how you measure distances and how you measure durations of clock seconds, that changes depending on your point of view in the universe, whether you are standing still, whether you are moving relative to something else. All measurements of time and space are relative and are dependent on each local observer. There is no synchronous clock striking time across the universe. There is no uniform ruler that gives us an absolute measurement to measure everything against. Everything is dependent on all the independent observers or entities and particles in the universe. Everyone gets their own clock. Everyone gets their own ruler. There are some universal things. There are some absolute truths in relativity. And in fact, it's the laws of physics are absolute. This is the key point to relativity, that no matter the observer, wherever you are in the universe, whatever you are doing in the universe, whatever you're having for dinner, whatever you're looking at, the laws of physics will always apply to you and they will always be true. And Einstein came to this realization because an earlier scientist, James Clerk Maxwell, had discovered that light, what we call light, light from a light bulb, the heat from a campfire, all that is actually a form of electromagnetic radiation, that waves of electricity and magnetism leapfrog against each other to create the light that we see in the universe. That was an amazing discovery. And Maxwell, in his calculations, discovered that light always travels at the same speed. It always travels at the same speed, regardless of the observer. We conducted many, many different kinds of experiments over the following decades in the late 1800s and confirmed this, that no matter what, light, whatever we try to do, light is always traveling at the same speed. And so Einstein enshrined this and used this as the basis for relativity. And one of the consequences of relativity is two things. One, you, an observer, no matter how fast you go, no matter how powerful you kick your rockets, you will, if you try to race a beam of light, if you start off a laser next to you and then you start running in parallel, you will never, ever, ever overtake that beam of light. In fact, you will never catch up to it. You can never achieve the speed of light. You will always be just a tiny bit slower than the speed of light. Another consequence of this relativity, which is baked into the mathematics, is that you will never, if something is passing close by you, say you've got a friend in a really fast bicycle or rocket ship or something, and it blasts by your face, you will never, ever measure that speed going by your face to be faster than the speed of light. It's just, you just can't. And this is interwoven. These concepts don't just stand as statements. Like Einstein came out, he came out in his bathrobe one day and said, "Hey world, you can't go faster than the speed of light." And then he saw a shadow and then there's 6 more weeks of winter. That's not
right.
It's worked into the very theory of relativity, which is one of the most tested theories in all of physics. We have tested every single corner and aspect of relativity. In fact, relativity forms itself as a cornerstone for all of our modern theories of physics. It could be wrong. Special relativity could be wrong. Of course, like all theories of physics could be wrong, could be updated in the future. Absolutely, of course. So far after a century of testing, we have seen no cracks whatsoever in the special theory of relativity. However, the special relativity is not the last word on motion in the universe. There is a broader theory, a more general theory of relativity. And in this general theory of relativity, also developed by Einstein, which is our modern conception of how gravity works, there are ways that you can move that you never violate those constraints, and yet you are still able to go very, very fast. For example, if I were to set up space-time around me in just the right way, where I crunch space-time in front of me and I extend space-time behind me, then I will move. I will feel a propulsion. I will feel an acceleration in the direction in front of me. At no point in this movement will I measure myself going faster than the speed of light. No other entity will observe me going faster than the speed of light. And yet, almost paradoxically, I can arrive at destinations faster than the speed of light. You can get around these special relativity restrictions by looking at a broader picture of how space and time work together. There are downsides.
Let me hold on. Let's not get too far ahead of our skis. Let's say that happened. How much energy would be needed to move and remove something in front of you and in back of you to arrive before light gets there? Is there enough energy in the universe to do something?
Well, this is exactly the problem. In order to make this kind of configuration of space-time, which in the one I'm talking about right now is known as the Alcubierre warp drive.
That's right.
Which is written by a physicist in the late 1990s, believe, who developed this concept. Not the first attempt to circumvent the speed of light. There, you can use wormholes to do it. There are other games you can play. In order to do this, in order to get this configuration of space-time, in order to make it happen, you need something very special sitting in the heart of your drive of your spaceship. You need something with negative mass. You need an object, an entity that weighs negative 5 pounds. In all our searchings of the cosmos, all of our understanding of physics, we have not encountered anything with negative mass. If negative mass were to exist, it would defy our common understanding of, say, conservation of momentum, where if you had a ball and it weighed negative 5 pounds, if you kicked it, it would fly backwards. If you dropped it, it would fly upwards. If you put negative and positive mass next to each other, they would actually react with each other and they would fly off to infinity with no input whatsoever. And so again, it's not that it's impossible for negative energy or negative mass entities to exist, but it requires a lot of updating. And as physicists, we're not afraid of that kind of updating. It's just, if you want to make that kind of update, you've got a lot of work to do. And every time we've tried to make those updates, like, oh, that'd be cool. I wonder if negative mass exists. Let's work it out in the theories. We run into a bunch of paradoxes and headaches and things that don't make any sense. And so for now, at least we say, well, negative mass appears to not exist in our universe. And then there are other issues too, that once you're able to go faster than the speed of light, you can start doing crazy things like violating causality. You can essentially send messages back in time. You can have causes coming after their effects. You can set up paradoxical situations. Once you're able to start traveling faster than the speed of light, you can start setting up mechanisms where if you launch your ship, then a message will travel back in time to hit the detonation button and blow up your ship. But the only way for the message to get there is for your ship to leave. But if your ship leaves, it means your ship was supposed to blow up. And that, if that sounds weird and complicated and paradoxical, it's because it is. And so.
But if the math supports it, then what do we do? And Brian Greene's latest research, he talks about this is what he's working on right now. And he made this statement a couple of months ago, and I'm serious. I listened to it 50 times to make sure I heard it correctly, right? His current research is that the math supports a hole where you can ask a question, it can go out to the edge of the universe, the answer to the question will be given to you before you write the question. Now, and I'm like, wait, what did you just say? Brian, pump the brakes, my man, right? Pump the brakes. And he said, look, I understand this is science fiction and this is crazy talk, but the math supports this, and I'm going to continue the research. And I said, now, I'm all about the crazy, but to have somebody that I consider pretty stable, right? Brian Greene,
stable genius, if you will.
Yeah. And but this is when we have the woo and we have the beer can that I just told you about, right? And then we have somebody that is so bright and so focused, like Brian Greene, suggesting something like this. I'll go back to my opening statement. Our two communities are going to hit head on at some point.
Yeah, I'm not familiar with that aspect of Brian's work. I do know there has been research into things like what these are called closed time-like curves. These are called there are various loop constructs you can put into general relativity that appear to allow time travel into the past or messages being sent into the past. You can have wormholes connecting like the inside of the interior of black holes to the exterior of black holes. Absolutely. I've encountered a lot of this kind of research in the past that where on the surface, it appears that, and this is a real thing, that there are constructs in general relativity that allow you to violate causality, that allow you to have messages and objects sent into their own past. In order to make this kind of stuff, yes, you can get the math to work, just like you can get the math to work of an Alcubierre drive. It requires some exotic substances in the universe that we're not exactly sure if those exotic substances exist. If those substances do exist, then yes, the logical outcome of the mathematics is that time travel into the past, etc., is possible. But right now, we don't know if those exotic substances exist, and we strongly suspect that they don't. We seem to have an understanding of causality. We could be wrong. Our understanding of the relationship between cause and effect in past, present, future could be all wrong, and causality is actually a much more tangled mess. As of right now, it doesn't seem like we're wrong. When it comes to questions like this, there's obviously something here to learn about the universe, but I'm not exactly sure what the universe is trying to tell us.
Yeah, and the ability, the whole. When I say, our community, it can seem whack. But some of the best science fiction out there, when you read it, and then you go, okay, all right, there's some bright minds that are working on this science fiction, whatever it is, Marvel comics, Marvel movies, right? They've got some wonderful science in there now, and somebody is paying attention. I appreciate that. But then when we go to something like observing, when you observe a particle and you can change its state, now we're talking, it's like telepathy or something. And the other side of it, where we have this mysterious thing called dark energy, and the universe expanding like it is, and that some say that the outer reaches is expanding faster than the speed of light. Now, it's not that they are traveling faster than the speed of light. The expansion is happening faster than the speed of light. It's not like planets are zipping past each other faster than the speed of light, but the expansion is. What do we observe with that expansion faster than the speed of light? Is it non-observable? Is it stepping over the edge of the cliff? And is that violating special relativity?
Oh, excellent question. And so that's when you brought up relativity and the restriction of the speed of light. That's why I was very, very quick, because I had a feeling you were going to go in this direction eventually. I was very, very quick to outline what special relativity actually says about this speed of light restriction, which is, one, if something's whizzing by your face, you'll never measure it to go faster than light. And two, if you try to race a beam of light, you'll never outrun it. When we look at galaxies, and I've used surveys, I've used data, measured the redshift, the recession velocity of distant galaxies. This is data I've personally collected, me and 1,000 other cosmologists have over the past few decades. Yes, we observe galaxies receding away from us faster than the speed of light. And that's not a problem. And there's two ways to look at this. And these two ways to look at this are exactly equivalent. It's just, it depends on which side of the equations you want to talk about and put into words. One way to say this is, yeah, special relativity is a local law of physics. You only are allowed to talk about stuff close to you in special relativity. Galaxies on the far side of the universe, we need a different theory to describe the behavior of those things. We have general relativity for that, and general relativity says, yeah, if you're on the other side of the universe, you can have whatever measured speed you want. Who cares? General relativity is cool. Another way to explain this observation, and again, this is exactly equivalent in the mathematics. I'm just putting different words on it or putting the emphasis on different parts of the equations, is to say velocity is something that happens through space. If I lay out a grid of space and time, and I have chess pieces moving through that fabric on that board, those chess pieces can never go faster than the speed of light. But if I am stretching the chessboard itself, then two chess pieces on that board will appear to get further away from each other, but they're not moving. If they draw an X on the chessboard underneath them, as I'm expanding this board, they will always see that X underneath them. They're not moving. They're saying, no, I'm not moving. How do I know? Because this X was right here a minute ago, and it's still right here. I haven't moved. They haven't moved. And yet, because of the expansion of the chessboard between us, we appear to be moving. So motion is only something that happens on top of the chessboard. Its motion is not defined to be something that the chessboard itself does. So we observe this. This is a normal consequence of living in an expanding universe. And it has a very, very real effect, especially in the long term. When we see a galaxy, a very, very distant galaxy, anything more than about 14 billion light years away is expanding, receding away from us faster than light, which is, by the way, the vast majority of the universe. When we see a galaxy, that light was emitted by the galaxy a very long time ago, billions of years ago. It took billions of years for that light to finally reach our telescopes and for us to see it. That galaxy right now, the light that it is emitting right now, in this instant, the light that it is emitting right now will never reach us. It will never, ever come to us. And so what this means is when we see a distant galaxy, over eons, over the next few billion years, and let's pretend we'll be around long enough to observe this, those galaxies will slowly dim, they will get redder, and they will eventually disappear from view. And over the long term, as our universe continues to expand, this will actually happen to almost every single galaxy that we can currently observe. Over the course of the next 10 to 20 billion years, almost every galaxy will be plucked from view. It will be pulled into this expansion as our universe ages, and we will never see those galaxies again. If you fast forward 20 billion years from now, our distant descendants existing in a Milky Way 20 billion years from now, they might see some nearby galaxies, a nearby cluster perhaps, but the trillions of galaxies that we currently observe in our universe will be gone forever.
So the deep field, right, which any one of those are some of the most amazing photographs ever taken in the history of everything. And I'm glad that we were here in the now in this time loop to have observed those. The thought of a deep field a billion years from now being black kind of freaks me out. But that's the universe that we live in.
And that's
right?
the name of your show.
Yeah, Fade to Black, right? What's the now? Okay. Is consciousness, there's a reason why I'm asking this. Oh, by the way, I love it when the word consciousness comes up and the scientist pulls back. Oh, shit, here we go. But I'm not bringing up philosophy, so we'll leave that go for now. I was just watching a movie the other day. You'll love this. Man, I should have wrote this down. I'm going to use this forever. This couple One is a college moral philosophy professor. Okay, that's the he. The she is a post-grad theoretical physicist employed at the university. Okay? They are dating.
The Big Bang Theory. I saw the show.
No. It's a movie.
Different one.
Right.
Okay,
You know
my
where I'm
bad.
going with this. So she goes, we need to break up. And he goes, why? Opposites attract. She goes, see, that's exactly it. We have nothing in common. And I love the line, right? And I was like, right, that's exactly the problem. We need more of opposites attract. But let's say that we have a situation of something more advanced than us. Then wouldn't they have the ability to understand consciousness and gravity, which we know virtually nothing about, by the way? Gravity, antimatter, dark energy, dark matter, that they would have a grip on these terms, and maybe the physics on their side of the universe is just a little bit different than ours, and they know how to go these vast distances of 10 billion light years in a second, like stepping through a door.
Yeah, you've opened up plenty of interesting, fruitful discussion points. One, when it comes to physics, we do believe that physics is universal across the universe. We've been working under this assumption ever since, like even before Newton. We're talking like Kepler and Galileo, that when we write down an equation for hydrogen atom, like a hydrogen atom here is the exact same as a hydrogen atom on the other side of the universe. We have tested this, like all assumptions in science. We don't just test our hypotheses, we also test our assumptions. And we've tested this. We've looked for evidence of, are we getting do different regions of the universe operate under different physical principles? Do they look different? Do they act different? Do they smell different? Were they different in the past? Or were they same in the past? As far as we can tell, physics, as we understand it, applies universally throughout the universe, which is pretty cool and also very powerful. When it comes to sophistication, technological sophistication, there's certainly more to learn about the universe. Our quest to understand physics is not nearly complete. We know of many of the shortcomings of our own theories of nature. We know the hard points. There's a long list of mysteries. There's a long list of things we don't understand. That's why I get to wake up every day and do my job, because we get to keep pushing and trying to understand this. Could it be that with a more advanced understanding of physics, chemistry, biology, or even a completely different way of approaching these kinds of puzzles would unlock some sort of mastery over space and time and distance and travel? Oh, absolutely. It's totally possible. I will be the first to admit that a new and revolutionary understanding of physics could bring about technology that might as well look like magic and miracles to us. That's absolutely absolutely possible. So I won't hold it out.
Okay.
Yeah.
Continue.
And then there are some other interesting questions, like, one, we also don't understand the nature of our own consciousness, which is perhaps an even bigger mystery than any mystery we try to tackle in physics, which is, how are we even able to dream up a thing such as physics? How are we able to explain what it's like to be ourselves? This is an enduring mystery in philosophy and scientific traditions, and also art and music. We are always constantly inquiring about the human condition and what makes us us. We don't know if consciousness is universal in the sense that any kind of creature arising on any kind of planet with any kind of underlying biochemistry or way of storing and transferring energy, once they become conscious, it's pretty much generic that their kind of self-awareness is the same kind of self-awareness that we have between our ears. We don't know that. We don't know if intelligence plays out the same way everywhere. So far, we only have one example of our kind of intelligence, which is us. And so we don't know.
Do you think, here it is, here's the deep philosophical existential question. And I love the thought experiment. Is consciousness physical? Is it chemistry? Or does it exist in the non-physical?
Yeah, beats me. I don't know. It's a fun question.
I know you think about it.
Of course I think about it. And it's possible to think about it and still not know and still not arrive at an answer or a conclusion and to toy with the various possibilities. I find, all the threads, this is a very long philosophical tradition. You said, let's leave philosophy out of it, but right. I actually, I have a PhD. My PhD is in physics, but PhD stands for philosophy doctor.
Yeah.
The old name for physics was natural philosopher. All scientists, we are a branch of philosophy. We are a
Why did you guys divorce?
Yeah, I don't know, because I like natural philosopher better. It's a better name. It's better branding.
Yeah. I mean, I always thought, you and I were talking about this earlier before the show, but I always thought that science and philosophy and anything progressive, moving, evolution forward, is about asking questions and thinking and wondering and pondering and going and exploring that. That we weren't going to divide this and separate this and move this in two directions. That some of the best parts of our history were philosophers were the original scientists. I mean, it's just like, and somewhere along the line, they just separated. Now there's a line in the sand. The Big Bang Theory, right?
You can blame the Germans in the 1800s. So they coined the term scientist as a contra to the word artist. Disciplines within science began to become, it's a weird grammatic construction, but it's getting late for me, so we'll go with it.
Yeah, that's fine. That's fine.
Became crystallized physics, chemistry, biology. And this, I believe, this is something that modern science lacks. But I want to add a caveat here. Scientists are enormously creative people. Scientists are enormously inquisitive, curious, imaginative people. You don't come up with quantum mechanics. You don't come up with relativity. You don't come up with modern cosmology without a little bit of pure imagination.
Right.
The practice of science, the practice of physics, really came into its own in the 1800s as a branch of philosophy that followed certain methodological rules where we use rationality, empiricism, a heavy emphasis on mathematics, logical consistency to explore the workings of nature, again, as a branch of philosophy. The earliest scientists, the people that we point to as the pioneers of the scientific revolution, people like Copernicus, Kepler, Newton, these people, even Galileo, these people would not be recognized as scientists today. They arrived at their conclusions not just from pure scientific reasoning that we would recognize today in the 21st century. They arrived at their conclusions from a complex interweaving web of thought and curiosity. One of my favorite examples is that Kepler's model of the solar system, where the planets move in ellipses instead of circles. He came to this because he was searching for harmonies in the motions of heavenly objects, the same way you would look for harmonies in music. He was searching for, in his words, the voice of God in the motion of heavenly objects, believed it was closely linked to music. That's how he landed on ellipses. The whole sun-centered model, heliocentric model of the universe, didn't come into fashion and become accepted, not because of like the weight of scientific evidence and rationality. It became commonly accepted because the math was easier for calculating horoscopes. And that's how the heliocentric model became popular, because the math was easy and everyone could do horoscopes super easy. Like,
I have a really cool telescope. I have a lot of things. I love going out and looking in my backyard. I look at what I have, and I'm such a doofus. And look at what Galileo was using. Just think about that for a second.
Roughly 8x, 8 times magnification.
Yeah. Okay. So in the little time that we have left, let me lay out a couple of things. Entanglement is not only faster than the speed of light, but it's at the speed of now. I have a hard time wrapping my head around that and how it can be observed at the speed of now and measured. Now, it's been tested over and over again. So it's not like this is some unproven theory or concept. Entanglement is generally accepted for what it is. Two particles react and change each other's state at the same time, no matter the distance and no matter what is in between. That's insanity.
Yeah.
Now,
welcome to quantum mechanics.
Right. Now, does that go against Einstein? Now, Einstein had major issues with it for sure. But how does this happen at the speed of now, a billion light years apart?
Yeah, so Einstein had major problems. He was actually one of the pioneers of quantum mechanics. And then in the span of a couple decades, he came to hate it. And in fact, another pioneer of quantum mechanics, Erwin Schrödinger of Schrödinger's equation, also came to hate quantum mechanics. He devised the whole cat in a box thought and experiment. He devised it to show how ridiculous quantum mechanics really was. Eventually, he just threw up his hands and he worked on other stuff. He completely gave up on the development of quantum mechanics. And part of it was over these reasons, these issues of entanglement. Like you said, entanglement appears to happen instantaneously, that when you take two particles and you bring them close together, physically close together, they end up sharing a single quantum state. And then if you pull them apart and do it very carefully, they can maintain this shared quantum state where the properties of one will automatically influence the properties of the other. Excuse me. This doesn't violate the speed. There's good news and bad news here. The good news is this doesn't violate the speed of light, because the speed of light is about sending messages. It's about sending information. It's about influencing one object sourced from another. And this entanglement, you can't actually use to send any information faster than the speed of light. That's because if I take these two particles, let's say I carefully prepare them, I carefully entangle them, and then we separate them, and I give one to you, and I keep one here. And you take yours home, which is thousands of miles away from my home. And then you open up your box and you start looking at your little entangled particle, and you see it going up, down, down. You see it moving. When you see it moving, you don't know, because of the very fundamentals of quantum mechanics, you don't know if it's moving because I'm over here in Connecticut and I'm wiggling my particle and it's entangled and I'm influencing you. That's one possibility of why you're seeing it move up and down. Another possibility is because of quantum mechanics, it's just moving up and down on its own. There's fundamental uncertainty. You're just going to observe a bunch of ups and downs. That's what particles do all the time. So you're going to sit there and record a bunch of 1, 0, up, up, down, 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 up, up, down. You don't know if that's a message coming from me, or if it's just random quantum fluctuations. The only way to verify is if I pick up the phone or I come on your show and I say, by the way, I totally forgot. I left the quantum particle entangled. I left it in the glove box. I totally forgot about it for a week. Everything you saw was just junk. Or I say, oh yeah, I've been trying to send you a message, buy my next book coming out March 5th, Rescuing Science, please, I was sending you this message. The only way to make that verification to actually exchange information is to do it the old fashioned way and exchange signals slow at the speed of light or slower. So
but there's an except here. There's a big except. You only need to know when the state started to change. And then you could see the repeating pattern. Okay.
I guarantee.
I understand the Schrodinger's cat scenario with this. I totally get it. But if you know the start of the state of change, then you could see the state of change from that point forward and make sense of it. And here's that's always been, I've tried to resolve this too a lot and think about it, but we're always talking about particle and particle. What if, now apply yourself to this for a second, the concept of telepathy or remote viewing, I think has a lot to do with the same ideas and principles of entanglement. And if you and I sat close, if we had the talent and we knew how to do this, and you and I sit close enough together and our brains become entangled, and then we separate ourselves, then we have a genuine share of information as opposed to one particle at a time. And the reason why I think like this, if there's an advanced ET civilization out there, more advanced than us, and they are 10,000 light years from their home planet on another planet, and they get a flat tire, they're not going to wait 10,000 years to call AAA. There has to be a way of communicating like that. And the only answer to that, to me, is entanglement. And they've got that figured out. And it's not done one particle at a time. And that's why science needs to think outside of the box to answer these very fundamental questions on how you would communicate across the universe if you are an advanced civilization.
I have a few responses. Let's start with the last part of your statement first, which is science came up with the very concept of entanglement in the first place. So we're already thinking outside of the box to even come up with a statement like that.
I agree.
And so, accusing scientists of not thinking outside the box when you're using the very statements produced by science to make that argument seems a little bit weird. Mm-hmm. It is perfect. Second, it is perfectly possible to entangle more than one particle at once. We have entangled systems of thousands of particles together. We call these Bose-Einstein condensates. And these are the foundation of quantum computing, is to entangle multiple particles at once. This is on the edge of modern research of trying to entangle as many particles as possible. Why in the examples I often science communicators use one particle at a time, it's just keeps the math easy and it keeps the examples very fluid and easy to talk about. You can certainly entangle many, many more particles. It's very difficult to entangle very large complex systems like the human brain, because as soon as particles, I spoke very carefully about these entangled states and that you have to prepare the system just right and you have to be very gentle as you're moving the particles, because as soon as the particles start interacting with other stuff, it essentially destroys the entanglement. There are so many interactions and chemical and physical interactions happening inside of your brain that any sense of entanglement is going to be very, very quickly lost. And then lastly, you mentioned like, oh, once you have the string started, once you know that I'm sending a message, then you know I'm sending the message and we're doing it faster than the speed of light. It doesn't work, because even once I tell you that I'm sending the message, you still don't know, because of the very mathematics that gives you entanglement also gives you the reality that you don't know if you're just looking at random fluctuations or if you're looking at an entangled situation. You have to cross-check with traditional communication channels to know that a message was sent. And this is the basis of quantum cryptography, where you do use entangled pairs to send messages, and you verify the message with traditional forms of communication. And then you know if the entanglement was broken, you know if someone eavesdropped on your communication. We have studied this for well over half a century, and the very mathematics that leads to the idea of entanglement precludes it as a form of faster than light communication. Now, there is very, very, very weird stuff happening with quantum mechanics. It appears, entanglement appears to be telling us that in some ways, at some level, physics is non-local, that physical systems don't have to be adjacent to each other in order to influence each other. And we don't fully understand that. We don't fully understand the implications of that, how it links up, if it links up to other fields of physics and understanding. The concept of entanglement, we just came up with it, 100 years ago. And like I said, science moves very slowly. This is a relatively new thing on the scene, this idea of entanglement. And we're absolutely still wrestling with it and trying to understand its full implications in the universe and in physical theories.
Yeah, right now we are entangled because you're answering my questions before I ask them. I love that, man. and see, and this is so. Let's get back to the actual fourth part of my ramble, which is there must be, not us, not with our level of being able to understand, but above us, there has to be a way to communicate in the now. You cannot wait for the speed of light within an emergency distress call. If you and I went out to Alpha Centauri, right, it's 4.5 light years away. It's next door. It's the closest thing. But if you and I get in trouble out there on our little Starship cruiser, we got to wait 9 years for an answer. 4.5 years one way and 4.5 years back. That's not going to work.
Yeah. Well, right? The universe is under no obligation to be convenient.
Why? and to that end, the other, I want to wrap with this. I never thought that I would arrive at the day where, oh, by the way, consciousness is dark energy. You heard it here first. That's my prediction. Yeah. Have you read Brian Greene's latest book, Until the End of Time?
I have not.
Okay. He kind of touches upon that in a weird way. Is this. I never thought that we would arrive at a point where there was actual conversation about whether the Big Bang actually happened now, where it seemed like we were pretty firm on that. And when I hear some very bright people go, well, man, maybe it didn't happen. Maybe forever is just forever. Maybe there isn't a star point. Maybe the universe has always been here. Does this surprise you? And does this go against? Does that answer why when we get closer and closer, running backwards, where the math starts to get a little fuzzy? And that would answer that. What do you think about these conversations that are happening now?
That's exactly it. And when we say things like the Big Bang never happened, we have to be very, very careful. Remember, science, one of the tools we have is to be very precise with our language, which is why we almost always just switch over to mathematics, because then we can be super precise and there's no ambiguity. But when we start attaching words to things, we have to be very careful about words like Big Bang. So the Big Bang is a model of the history of the universe that says, in general, that a long time ago, the universe was smaller and hotter and denser, and that over time it has expanded and cooled to arrive at its present state, and it continues to expand and will keep getting colder. That's the Big Bang. So all our evidence, and we have a lot, points to this model being correct. There's lots of bits we don't understand for sure, like any scientific theory, but there's a lot of evidence to support this overall picture. And so you can't say like, well, the Big Bang never happened. Like, we live in an expanding universe, and, somehow you need to generate an expanding universe. Good luck, trying to come up with an alternative explanation. But there are shortcomings to this theory, and we know that the theory breaks down in the earliest moments of the universe. At a certain time scale, at a certain size scale, things are so small, so hot, so dense that we have no physical theory to describe it. All of our mathematics just breaks down. Everything throws up infinities. We have no idea what's going on. We genuinely have no idea what the earliest moments of the universe was like. And in fact, because those moments were so extreme, we don't even know if phrases like earliest, beginning, scale, all these normal attributions we give to space and time even make sense at those scales. I just did it again. Like, we don't even know if there are basic fundamental conceptions of space and time are even relevant at the earliest moments of the Big Bang. It's perfectly possible that there is some other kind of universe or some larger structure or some sort of progenitor that gave rise to what we call, say, the traditional Big Bang, the hot, dense, expanding universe that appears to us, 13.77 billion years ago. We don't know. There's some very, very cool, intriguing ideas out there. These are at the edge or even a little bit beyond the edge of our understanding of physics. Very deeply hypothetical, very theoretical, very fun and interesting to explore and play with and try to search for ways to observationally verify them. It's definitely fun to think about. And these two concepts are not incompatible, that the Big Bang totally happened, and that there's more to the story.
Is it possible? So if we take, let me back up. If one little number is off, gravity's just a little bit different. If anything, what at that moment, then the Big Bang is a big doesn't even happen, and you and I aren't talking right now. So I often wonder how many Big Bangs start but don't grow up. That, you know what I mean? That there's just something just a little off, just a little, not enough gravity, not enough hydrogen at that moment, whatever it is, that something just, and the start happens, but it's just a little and just goes. And if that is the case, how many times could this have happened throughout not only our 13.8 billion years, but infinity? Forever is a long time. And how many more times this could occur and how many times they are successful? I wouldn't suggest the multiverse, but it kind of leans like that to me, in that direction where these ideas start to become reality for me.
Yeah, that's definitely a puzzle, because obviously the universe is tuned or appears to be tuned to our kind of life. Because if you were to change, like you mentioned, the strength of gravity, the mass of the electron, the speed of light, the number of dimensions, then our kind of the basic physics and chemistry and biochemistry that gives rise to us would be just outright impossible. It's open We don't know if other kinds of life that don't rely on this kind of biochemistry or this kinds of physics would be impossible. So if we found, there might be, you can imagine this thought experiment, an alternative universe where gravity is super strong and it lasts for, 10 to the minus 15 seconds of femtosecond, and there is some sort of conscious entity during that femtosecond that's sipping its version of morning coffee saying, whoa, could you imagine if gravity was so much weaker and there was this giant empty cold universe, and that would be completely hostile to life, right? And it's wondering about us and thinking there's no way that life could exist in a universe like ours. We don't know enough about physics. We don't know enough about life in order to answer that kind of question. We don't know if the universe is tuned somehow, or if it's somehow generic, or if there are rules that we have yet to discern that do determine that gravity is this way, the electron mass is that way, the speed of light is like this, the number of dimensions like this, that there is some higher level understanding of physics that would reveal why the universe has the properties that it has. We don't have access to that higher level understanding, at least not yet. And so the best we can say is this universe is pretty great. I wouldn't want to live anywhere else. And we don't know if this is the only universe there is or if there's more out there.
Now, why? And let's end on some laughter. Okay. By the way, perfect conversation tonight. I just a perfect conversation. Why is it that in order to get a physicist to laugh, you only have to say free will?
I don't laugh at free will. I laugh at many other things. My kids make me laugh all the time. My wife makes me laugh. I come up with clever jokes and I tell it in front of my students and I crack myself up, and they don't laugh. I do not appreciate their lack of humor at my horrible jokes. I would tell it to you, but I wouldn't want to embarrass you on this show.
But like, and you know where I'm going, and it's just a strange thing to me where you get a couple of theoretical physicists together, and eventually the subject of free will comes up, and there's I knew you were going to ask me that. You didn't have a choice, right? And I'm really weird with it in that I understand the deterministic mathematical way of particles and combination and gravity and this and that, and everything is inevitable, and star systems and circular dust rings and the creation of planets, and everything's going to happen a certain way, and eventually it's going to roll down to the micro of me. And whatever I'm going to do is going to happen. It's just the way it is. And then there's the other side of me that says, I'd like to think I want chocolate ice cream today because it was my decision. And this wasn't predetermined by math. Mm-hmm. It's weird. I'm in the middle with it. Where do you lie?
Where I personally lie, and there's this temptation, especially among physicists, to say everything is determined. It's a clockwork universe. If you can just write down, the current state of the universe, you can project it out infinitely far in the future and make perfect predictions. This breaks down even in physics. It breaks down with quantum mechanics. It breaks down with chaos theory. There are so many cases where we cannot make predictions about the future. And where I personally lean on the free will spectrum, and so you'll encounter some physicists who say, everything's just super determined and since the beginning of time. That's a very minority opinion. Most physicists actually don't even think about free will all that much. Where I lean on it is I tend to go along with the general consensus, or I should say, the most commonly accepted idea amongst philosophers, which is an idea called compatibilism, which is to say, okay, let's say I'm trying to pick what's for dinner, and I have two choices, the steak or the chicken. And I make a choice. I close my eyes. I'm thinking, I'm going to have the chicken. And I sit down and I eat the chicken. There is nothing incompatible with the laws of physics with that choice. Like you can trace back all the ions in my brain, arriving at this. Okay, and imagine the alternative where I pick the steak. There's also nothing incompatible with the laws of physics in the universe where I pick the steak. The only problem or the only issue might be the actual act of the choice, but the consequence of both choices is totally fine with physics. So maybe just going out on a limb here, maybe we don't understand all of physics. Maybe there's yet again a deeper understanding of physics, a higher level understanding of nature, where we would discover in those new laws of physics, choices are totally compatible with a better understanding of physics. Maybe these questions, and that's why I love these questions like this, like free will poses such a paradox. Paradoxes are not sources of angst. These are sources of joy. These are places where nature is telling us there is yet more to discover. There is yet more to learn. And so let's dive head deep into the paradoxes and the contradictions, because that's where we get to hopefully learn something new.
Is staying on this for a second. And we're at the end of the show, and it's a complex question with hopefully a simple answer, because it's about entropy. Mm-hmm. And it is a word now where we have a scientific definition and we have a pop culture definition of it. But in a nutshell, it seems to me that entropy makes sense and ultimately is inevitable. I get that part of it. But if you slow down time in your own world, you can remove entropy by not having complications and not adding to the complexities of life. And maybe if you look at it that way, you can slow down entropy, or maybe have it stop. Is it possible, or are we just stuck in the second law and eventually everything is going to unravel?
You can absolutely have local reversals of entropy. You can have order from disorder. For example, the appearance of life on Earth. There's a lot of order going on in life. We are going against the grain. We are reversing entropy here on Earth. But nothing comes without a cost. Our increase of entropy here on Earth, on the surface, is all powered by the sun. It's balanced by an increase in entropy within the sun. And so globally across the universe, entropy is always going up. You can make local reductions in entropy all you want, but somebody somewhere is going to pay for it.
Yeah. And when are we, the answer to that always is, as stable as our sun has been for 5 billion years, right? That's pretty stable, right? It's a smooth, it's a smooth part of entropy, but it's going to end in a bad way. And eventually we have to blow this popsicle stand. We can't stay here.
Yeah,
that's it.
We got a few billion years to figure it out, so we can take our time to do it right.
Hey, Paul. Perfect night, my brother. Thank you so much. And hey, the next time that you're on, we do need to jump into entropy and some other concepts like that, and certainly colonizing the Milky Way and figuring that part out too as well.
Let's get out of here.
Thank you, Paul. Behave and be well. Enjoy the rest of your night and your weekend.
Thank you.
Dr. Paul Sutter, pmsutter.com. The links are below, and we've got it over on social media and, of course, on our website. What a great night. What a perfect night on the show. And for me, as everybody knows, this is officially the start of my weekend. Yeah, we have a great week next week on Fade to Black, by the way. Fade to Black is produced by Hilton J. Palm, Renee Newman, and Michelle Freed. Thank you to Bill. Thank you, Jonathan. Thank you, Dennis. Thank you, Kevin. Webmaster is Drew the Geek. Music, Doug Aldrich. Intro, Spaceboys, spaceboymusic.com. Fade to Black is produced by KJCR for the Game Changer Network, and this broadcast is owned and copyrighted 2024 by Fade to Black and the Game Changer Network, Inc. It cannot be downloaded, rebroadcast, copied, or used anywhere in the known universe without written permission from Fade to Black or the Game Changer Network. I'm your host, Jimmy Church. Until Monday, I want you to have a great, safe, fun, and amazing weekend. With that, go Backley Tappy.